Right. So I'll start. I'm recording with a different software as well. But that's me. Doing screen two. All right. Hi, everyone. Thanks for joining and thanks for sticking with it. And I hope everyone's able to hear me and give a shout if there's any the sound drops or anything like that. I'm trying to use my headphones and I didn't last time. Oh, great. Thanks. So I'm going to turn my camera off because I'm going to be looking at another screen and it's going to look like I'm looking in the wrong place. I'll do that. Hope everybody's doing well. And yeah, thanks for joining on a Friday afternoon. And I hope we can keep digging more and more into this and things become more and more clear as we go over them in different iterations. So, I just wanted to take a minute to get people thinking about what we talked about last week, just to shift our minds, because I'm sure everybody's coming in from other meetings, other commitments, and what have you. So just to bring ourselves here, is there anything that stuck with people from last week? Anything that jumped out at you that you remember from last week that you thought was new or interesting, or you had a big question about? I wanted to give a moment for that.
Yes, I think I can start on my side. I think as a start, I think you've seen my sort of background in terms of what we submitted prior to our first session. I think
Yes.
it provided, I think, some better understanding, especially in terms of the what modeling is, and the A, Bs, and Cs of it. I think really, especially in the initial start of what you presented, really did, I think, shine a light in terms of me having a better understanding. And then I think it shifted and went into me requiring a bit more focus in terms of when we delved into the platform itself and the various functions. But yeah, I think it really did assist in terms of just a better or an improved understanding than the one that I initially had.
Oh, great. That's good to hear, Sunil. And with some of the nuts and bolts, like we're gonna see things over and over. I believe in. I think these things need a lot of repetition for everyone. And also something to say also is that, like, not everyone needs to understand every little piece of this. The more you understand, the better, obviously. But it is like a team thing, and I foresee that an organization like this, some people are going to be more on like looking at what data needs to go into the model from where and that kind of stuff. And some people are more going to be running the software, and some people are going to be making other kinds of decisions about how we look at the outputs and stuff. So, but the more understanding everyone has, like, the better it can work together. And hopefully as a group can run this beast. They're always like this though. Like, every modeling software, not SWAT may sound particularly complicated, but they all actually, none of them are really much less complicated. So. Did anybody else have things that stood out to them, things they remember from last week that stood out to you or that you wanted to ask about? You can also stop me later, but I wanted to just pause for that first. I'm not hearing anything, but was anybody about to say something? I think I'll go ahead and move on. Thank you, Sanela. And yeah, I don't feel. Oh, Sanela, you gotta say something? So you unmuted.
Yes. No, I think prior to now session, but I'm not sure why Ndombi is not raising your hand. But it's just in terms of interest in terms of where we'll start off from today, because I think she was trying to join the dots from our last session because she was faced with a couple of difficulties in terms of the exercise that we sort of were doing towards the end.
Right. Yes. Okay. That's step four. So
Um,
for oh, sorry, go for it and tell me.
Hi, Julia. I don't know why Sanel is telling on me, but so there was a step that I skipped initially, so I started again, and it seems to be working just fine because it was giving me an error when I was creating the watersheds, but now it's fine. Thank you so much, Sanel and Julia. Thank
No,
you.
no worries. That's great. Now I'm gonna come to that. I'm gonna ask how far along everyone got to. But I'll get there because we'll spend a bit of time depending on how far along people got with the exercise, and then we'll delve into like looking at the what all those bits mean. Yeah. So great. I'm gonna go ahead. So we're going to have a bit more. So just as a recap of where we are, we're still working on this part of looking at, like background concepts that are going to help us in theory on how to set the model up and then how the software works. And then depending on how things go today, I think from next week, if not next week, from the week after, probably next week, we'll start delving into the specific decisions for modeling the catchments for uMngeni water and uThukela water. Um, yeah, in terms of what input data to use and that kind of those elements. But we're still at the basics or the background part today. And in terms, just to remind everyone, I will be sharing recordings as well. And Cornelia helped me set up. There's a Google Drive that's shared between EcoSource and uMngeni water, and I will put things there from now and test out putting things on YouTube as well. And again, feel free, like I'll try and see raised hands, but sometimes I've got a few windows open at the same time. And if I don't see you, like please just feel free to unmute and interrupt. It's not so formal. And then I'll make an edited version of recordings and stuff if we need to make it easier.
Yes. Sorry,
so we
Julia,
can wander. Yeah, go for it.
Yeah. So with that Google Drive, I just was possibly a request from to Cornelia to have us added because I think it's only a select few of us that have access to it.
I should be able to share that subfolder with you myself now. I've been given
Yes. Okay.
right.
Okay.
So what I'll do is once I put the new recording for today in there, I will share the subfolder for this training with everybody in the group. And then you
Okay.
should be able to get everything in the folder. Because I checked, I saw that I could change the share settings myself. If I'm not able to, I will get back in touch with Cornelia to help me do that. But I think I'm able to do it now.
Okay. Thank you.
Yeah, I think that'll make that part easier. Thanks. And then, yeah, as I mentioned, there's lots of resources on SWAT out there, like loads of, so there's video. I learn better by reading myself, but a lot of people like YouTube videos and stuff, and there are quite a few out there that people make. So just to let you know that. So for today, I'm going to do a recap of some of the stuff on session 1 with a few additions. I won't spend too long on it, but I think it helps to recap before going on to how the water quality modeling is handled, and how SWAT does that part. And then we'll spend time going into the tutorial, see how far people got, and talk, like I'll show more of the back end of where files are ending up and what the input file structures look like and that kind of stuff. I wanted to ask, I can do, like last time I did 2 breaks. I feel like 3 hours is a long time and people need to get up and move and stuff, but I can also do, if people prefer, I can do 1 longer break in the middle, or was 2 breaks okay with people? Did anybody have a preference there?
A longer break would be nice.
Cool. Is anybody disagree? I'm happy to do 1 longer break in the middle as well.
Yes.
Yeah, no, sometimes like the kitchen's far away or the bathroom's far away. All right, need to make a phone call or something. Okay, so I will do a longer break at around 2:30 as close to as a section break. We are there. Thanks, I'll do that rather. All right, so I'm just going to recap some of the stuff from session 1 quickly. And then we can, and then add, like, layer on some things that are relevant to the water quality piece. So we talked about background of hydrological modeling theory, sort of overview of quite a lot of elements, and then started talking about how SWAT Plus in particular addresses these elements, like breaking up the catchment into pieces and representing the different processes that allow water to flow through a catchment. And then we started a little bit on the software structure in the tutorial. So we also talked about sort of the overarching process of doing a modeling project anyway, and that it needs to be driven by the goals of the project and be aware of what data is available in the first place. And then we build our model and we see how good is it, and then we have to communicate the outputs. And we talked a bit about this is all being based on an understanding of the catchment water balance, where there's inputs and outputs and storages. And when your inputs and your outputs don't equal, you change the amount in storage. So soil moisture storage can go up or down, groundwater storage can go up or down, your reservoir storages can go up or down based on inputs versus the outputs. And if we rearrange that equation, we get to sort of the basic equations that give us the outputs that we're interested based on the inputs that we know we have data on, and the representation of these processes. So when I say processes, I mean like rainfall and then interception of water by the canopy. Then you have throughfall onto the soil surface. Then when it hits the soil surface, water can infiltrate or it can run off. And then once it's water that's in the soil can percolate down or it can flow laterally through the landscape. And then if it percolates downward, it can end up recharging a groundwater aquifer and it can flow from there. Either it can sit there, it can be accessed by the vegetation or not, it can add to the stream or not, it can flow if there's a gradient. So when I say representing processes, those are the various processes we're talking about. That will determine the balance between inputs and outputs and storages. So the numerical model is basically a set of, you have a structure like these units that we're modeling, and there are equations that represent those processes to get to what the model outputs. And people usually think of just the stream flow, but the model is also actually calculating how much evapotranspiration is going on, soil moisture storage, groundwater storage. So those are all like actually outputs of the model as well. It's just people don't often always look at them, but it can help you to look at what it's doing there, see if those are realistic as well as the stream flow being realistic. So we have the thing, we have the numerical model is going to have a structure to it. That's how we break up the landscape and we break up the river system into units, and we break up the soils and aquifers into units. And then we have equations, algorithms, and we have parameters that are values that are used in those equations that are assumed to be somewhat static, but you also have these input variables that have a time series element to them, like rain, the climate's inputs. But other things that also have time series are things like irrigation and water transfers, point source outputs. Those are the input variables or input data as well, time series data. And then we have our outputs that often come as time series as well. So the stream flow, evapotranspiration, groundwater storage on each given day. And so to do this modeling, we need various input data. We need climate data, rainfall, and then we need data about the catchment and about like the land cover properties, the soil properties, geology properties, channel properties, and also the external inputs, withdrawals, transfers, dams, irrigation. And then we also need data that we can use to check how well the model is performing. So stream flow, what is generally used, but also soil moisture, groundwater, and AET. But you can also use water quality if you do a water quality model to judge how well your model is doing on that part. So we use all this data to determine the structure and the parameter values, especially the land cover, the soils, and the geology get used to determine the structure and the parameter values. Oh, and properties of the channel network. So we talked about how SWAT does that. SWAT breaks the catchment up into subcatchments. In the SWAT terminology, they say watersheds, and I think they also say basins. So it's the same thing as catchments there. And you start by delineating a stream network, and there'll be units in the stream network, and they get called channels in SWAT, and then streams are bigger channels. It will create a subcatchment for every confluence between two streams. You can choose to have this like streams and channels, or just have streams, and we'll look at that in the tutorial. And then you can also add in specific points where you want it to break in addition, like make a new subcatchment in addition to the confluences. And that could be a point where you have a weir or a monitoring point that's not like right near the confluence of two streams. So then it makes a subcatchment, these red outlines, for each stream unit. And then those subcatchments are divided into HRUs that we talked about that feed, each HRU will feed a specific stream or channel unit. And then their aquifers in SWAT, those are subcatchment based. So unless you subdivide the subcatchment, again, which I'll show you in a sec, you will have one shallow aquifer and one deep aquifer for the entire subcatchment. All the HRUs that overlie it, the recharge from them will go into that one shallow aquifer reservoir. So the HRUs, those combinations of topography, land cover, and soils into these units, they are used to calculate the surface and the shallow subsurface processes. So when I say surface and shallow subsurface processes, I mean like the canopy interception, the infiltration of water, runoff, surface runoff generation, movement of water through the soil, and then percolation and recharge into groundwater, or lateral flow. So in SWAT, it gets called lateral flow, depending on where you study hydrology and what you read. And like some people call it interflow, some people call it shallow subsurface flow. It's essentially that flow in the soil or at the soil rock boundary that's above where the aquifer lies. And some catchments have a lot of it, and some catchments it's not really a significant factor. So I wanted to make how we think about this part a little bit more concrete, this delineation of HRUs. So it's picking out units of similar topography, vegetation, and soil, such that it's reasonable to calculate these processes, so like infiltration versus runoff, evapotranspiration, recharge, for that whole area as like a single unit. So if I look at an area like this, for example, it makes sense to use topography quite strongly because there's an association between topography and land cover and vegetation and soil properties, and also how people use the land too. We tend to do things differently on flats versus highly sloped ground as well. So in this kind of a landscape with not many other interventions going on, like one HRU could be the crest and plateau area that looks like it has grassland primarily, and medium to shallow soil depth. Then you have this cliff area that's super steep, little to no vegetation, little to no soil, so it'd probably be almost impervious, maybe some infiltration into the fractured rock, but it's so steep, probably wouldn't. You might have water flowing out of it. And then below that, we've got like a hill slope area that's got woody vegetation. It probably has a medium soil depth. And then there's not much of a valley floor in this particular valley reach, but if it was a bit wider, you might have sort of valley floor area with a slightly different vegetation, woody vegetation type, mostly it looks like here, and it would probably have a deeper soil than the hill slope, for example. So here you could have, 4 HRUs potentially that get modeled separately and linked to each other to feed that stream. That's quite a simple one. If we look at, and then, as we start getting more land uses and more things, it gets trickier. And we also have to consider when we're delineating our HRUs, are there differences in land management that we want to make a separate HRU for areas that are managed differently? And also from a water quality point of view. So like here, there seem to be hill slope areas with, you could lump, depending on the spatial resolution you're using, you could either pick out the woody areas, or you could make one area that's sort of mixed grass and woody with medium soil depth. You could delineate the valley floor. I see a patch of riparian vegetation there. It gets narrower and wider in different places. You have sort of this hill slope that's just grassland over here on the left. You have on some gentle sloping land, there's maize that's not irrigated in this case, may or may not be fertilized, and it would help to know that. And so then if you had like a large area of an agricultural type, you might want to break it into subclasses that are fertilized, not fertilized, irrigated, not irrigated, in as much as we have information to do that. But we'll come back to that when we're looking at our models for the uMngeni area, uMngeni water and uThukela. And then also with settlement areas, like for this picture, it's low density. There's very little. Sorry, I messed up the wording there. I'll go fix it. This is very hard surface. I meant very little hard surface, very little impervious cover. So in this case, it may or may not be worth pulling that out and representing it separately, because it might be such a small area in the landscape, and the settlement looks quite pervious. So it could almost be like it was a quasi-wooded area. Unless there's something specific about this from a water quality point of view that we needed to represent, if there's a septic system or something. But then if you start getting to other kinds of landscapes where there's a bit more development, you might want to delineate things differently. You have like in this picture, you'd have a crest and a hill slope as a grassland, have some information about the soil depth. Then in this foreground, it gets pretty messy. So you'd have to decide, like, how are we going to represent this with units that we do calculations for? So like you could represent much of this hill slope as medium to low density development. I was eyeballing like maybe 50% hardened surfaces. There seems to be a lot of, I think that's eucalyptus. You'd want to know a little bit if, depending on how big of an area this is, if it has what kind of sewage system, are there water quality elements we need to represent about this more developed area. And then if you wanted to, depending how fine we're going with the spatial resolution of the model, you could sort of pull out some of these more consolidated treed areas in between the development as separate HRUs. And then there is a bit of a valley floor area. There's some woody, there's some reeds. If there was more of this reed area further up, you might want to separate it because it has very different evapotranspiration than the trees. Yeah, so you can see how I bring this up because I want people to think as you're moving around in your catchment areas, like we can't pull out and represent everything separately, because then the model becomes huge and it takes days to run it. So you have to lump things to some degree, but we also don't want to lump things so much that we can't ask the management questions we want to ask with the model. And so there is the national land cover data sets, land cover types, and then there's other land cover mapping for KZN that some of you may or may not have worked with. And so we'll have a discussion later on in the course about what land cover types and soil types should we be using in our case, particularly for the settled areas. in terms of what water quality, and some of the agricultural areas too, in terms of what kind of management parameters we can apply to those areas that are different from other areas. Or if there's, areas of known, like more like sewage systems or more leaks or less leaks, and the formal and informal sewage systems and that kind of stuff. So I just want to just introduce this, and as we go through examples of delineating HRUs, and we're talking about this kind of abstractly, you can think about it more and more for the landscapes you're working in. So then we would delineate these HRUs, these groups. So let's say here there's like 4 or 5 of them again. For each one of those, we'd calculate all these shallow and surface and shallow subsurface processes by the HRU level. And one thing that I didn't talk about last time is that SWAT also calculates plant growth for these HRUs with some parameters for the vegetation types. There's a lot of default parameters. We don't have to get too much into this, and it doesn't impact the hydrology so much. You do have to look at the back end of the model and make sure all your vegetation didn't die. It can actually, you don't set the parameters right, and then suddenly there's no evapotranspiration losses because it assumed the vegetation was all harvested or might have gotten too water stressed and stuff like that. So we'll look at that later, but so as part of what it calculates for the hydrology of HRUs, it does consider a bit of plant growth, and that's part of its crop modeling. And we won't be using the crop modeling necessarily here, but it does affect the hydrology and it does affect the water quality. So that's also calculated as part of the surface and shallow subsurface processes for each HRU. And then there's the question of linking the HRUs to the stream. And there's different options on how to do that. And the tutorial and what I think we should do for the models for the uMngeni water catchments would be this next layer of way that we link them. So I'll go into that option now. So original HRU models and like the original ACRU model and the older SWAT models, they did this thing called parallel routing. So you do all these calculations by HRU, and then you work out how much surface runoff, lateral runoff would come off of each one of them, lateral flow runoff. And you would add all of that into the stream in a parallel sense. Like they don't run from one to the other to the other. It's all just added to the stream. You can add some delay functions if you think it's very far away from the stream, but the delay functions they don't talk to one another necessarily. It doesn't know how much runoff comes off the cliff or how much runoff comes off the hill slope. Doesn't have anything to do with how much runoff comes off the cliff mathematically in this setting, in this way of doing it, parallel routing. And then series routing routes one from the next to the next to the next, but they're not always in the actual landscape. They're not always cleanly in that order, like crest, hill, slope, cliff, valley, floor, for example. So it's a bit tricky to do that neatly, but it does allow you to do a spatial arrangement. It's more computationally intensive as well, because you have to see what happens to the runoff water. Like when it goes from the crest to the hill slope, does it infiltrate when it gets there or keep running off? And you have to do the calculations of that. But that is to some degree what's happening in the real landscape. So SWAT Plus has the basic approach in SWAT had been this parallel routing, which has pros and cons, and you can get reasonable results from it, but you have to take some workarounds to represent things like buffers for water quality. Like if you have a riparian buffer area and stuff like that, you have to add little extra modules to be able to represent that. But now SWAT Plus, which is the newer model, it adds this optional extra delineation in the subcatchment of what they now call landscape units. So this is a bit of a repeat, but I think it's important. And then you do this in the tutorial as well. And it delineates subcatchments into upland areas and floodplain areas, and use the topography to do that in different ways. And then those different landscape units feed to their channel reaches, but the HRUs within them, within the upland and the floodplain area of the subcatchment, have a different routing. So they're routed that all the ones that are in the upland area, the runoff from those are gathered together, and some of it will flow onto the floodplain, the HRUs that are in the floodplain landscape unit. I've just shown one here, but it could be more because you could have some agricultural area in the valley floor. You could have some wetland and some grassland, and there could be multiple HRUs in here, but it would lump everything from the uplands, spread it out on the floodplain, and you can control how that's done. Some of it can overflow directly to the stream channel, or some of it can be spread out here. And there's different ways of controlling that in SWAT. But this would be the routing of water and water quality parameter pollutants and other elements through the landscape. SWAT doesn't offer that direct series routing that I showed you, but it does offer this, which is kind of a helpful medium approach. And for those of you that have used ACRU offers something like this as well. Actually, they have a special floodplain HRU you can add that would get some of the upland flow routed to it. So that's similar for those of you who have seen that. So looking at it more like in a sideways way, you could have these HRUs in the uplands, and then you have the floodplain one, the cross-section view, I should say. And the aquifers are also, when you do this landscape unit delineation division, you also do now like 2 aquifers per subcatchment. Which I think is useful because actually you can have this floodplain aquifer that can be quite different than the upland aquifer. It's often like groundwater in the sand, in a sandy valley deposit. Again, with this routing again. So all the HRUs that are in the uplands would recharge this upland shallow aquifer. All the HRUs that are in the lowland or the floodplain recharge this floodplain shallow aquifer, and then water can flow from the upland shallow aquifer to the floodplain one and then to the stream in terms of groundwater flow. And then the deep aquifer in SWAT is not really, it doesn't interact with the stream. So once things recharge there, it's kind of like a net loss to the catchment system. So you can choose whether any water actually goes there or not, depending on what you think is going on. And we'll get to that later. So yeah, so you end up with these 2 aquifers as well when you do this. This is just showing that pictorially again, that you have bigger aquifer units and smaller surface units, your HRUs, and then the bigger, and this picture is from Mike Shee, but it also applies to what SWAT's doing as well. So you have these aquifer processes are calculated at the scale of the subcatchment or at the scale of the landscape unit, as I showed before with the upland and the floodplain aquifers as being 2 separate aquifers that flow into one another. That division here for the groundwater processes. So that's like flow towards the stream or recharging the steep aquifer that essentially is seen as a loss. And then the model also has the flow network of channels, and that can have water bodies on it, and it tracks, which channel flows into which channel flows into which channel, and which ones connect to what water bodies and how do those overflow. And in terms of channel routing, each channel unit has an inflow and an outflow, and the inflow will be everything from all the HRUs that feed into it and the aquifers that feed into it. And then transfers, point sources, and reservoir outflows that enter that channel unit. And then outflows to the next downstream channel unit would account for the flow rate. If it would all flow through in one day, the inflow would pretty much equal the outflow unless there are other losses. But if it's a big, long channel that flows very slowly and it takes more than a day to go from the upper point to the outlet point, you could have some essentially storage in the channel for that day that only leaves the next day. So it accounts for the flow rate, and it would be also the length of the channel there. And then evaporative losses off of the channel, transmission losses with water infiltrating into the bank if you allow that, and then withdrawals that may happen along the reach from the inflow point to the outflow point. And so there are channel dimensions in SWAT, and then if there's so much water, like it has a basic channel dimension, it assumes they get bigger and bigger as it goes downstream. If we actually have information about the sizes of the channels, we can input that. Otherwise, it makes assumptions for you. And then if it gets so big, like if there's extra water that overflows this, it makes a hypothetical floodplain to do these inflow-outflow calculations. But it doesn't know what's on that floodplain, so it makes assumptions. It doesn't actually track what land covers are on the floodplain. But that's just for the flow routing, how long it takes for water to get from A to B, but it also affects some of the water quality calculations. And then you have these water bodies of different types that are along that streamflow network. So there's none of those in the tutorial, but we'll get in how to do that with an example from one of your catchments. We'll do when we add reservoirs and go through the rules for that on another day. So actually, before I go on, are there any questions about this recap of the structural stuff? I hope this is useful. I know I did cover some of this last week, but I think we're adding layers to it.
Yes, no, I think it's quite clear on my side. Mine was just the interest in terms of those land use classifications. So that is already sort of fed using well into the model prior to you running it. So does it like come standard as prepackaged, or is it something that we also need to add in as part of the input process?
Yeah, so it is part of the input. So we have to decide what land cover map to use. So we need to, so in the tutorial, the land cover map has already been prepared. The tutorial is mostly just to show you the software structure. But as we go through it, I will point out, what we'll have to prepare for. And I've already set up a functional model in SWAT. I'm moving it over to SWAT Plus. So I've gone through this for your catchments already. But in this redoing and moving it to SWAT Plus, I'd like to engage everyone and get more input on how. So I've done one iteration of deciding all of these things for your catchments already, but I'm moving the model over to SWAT Plus. And I thought while I'm doing that, it would help to get everybody more input on how we do that. So to set up the model in SWAT, you need to prepare a land cover map, which includes the classes that you want to include. And where we get the data for that, there's the national land cover data sets for different years. So there's also the timing of the land cover map because land cover changes. And then there's things that does and doesn't include. So I'm going to have a session where we actually look at different land cover maps. And I'll show you the decisions I made in the previous round. And we can see if we want to change any of those in terms of which land cover classes are included in the model. Because I don't know if anybody's worked with the national land cover data sets before. For South Africa, they make them every couple of years now. They've tried to standardize the method, but there are 72 classes. And not all 72 classes are present in these catchments, but there's still a lot. And if you do 72 classes times however many soil types you want to do, divided by times how many subcatchments you want to do, you end up with huge amounts of HRUs. You actually have to assign property parameters to each land cover class in SWAT as well. So it is worth lumping some of those that we think are reasonably similar and we don't need to divide them for any particular reason. But we do want to keep some of them divided as separate, like development type, like residential types or those kinds of things. So there's this process of which ones do we represent individually and which ones can we lump? Like, are there different kinds of woodlands that we can lump into one class to represent it as one thing? Even though we know it's not really one thing, but if we represent everything, we'll never be able to run the model. So it's these decisions that you have to make. So SWAT doesn't do that. You have to give it a land cover map. Likewise, you also have to give it a soil type map. And then you also have to give it property values, and it has databases. So the next thing I wanted to actually get, so it was a good timing of a question. So I wanted to look again at some of the process equations that it has in it. I'm not going to go through all, there's way too much to go into every one of them, but it does give you an idea of what we need to think about when we're deciding on these land cover classes and these soil classes and aquifers already. So There's some parameters in the model that it calculates for you based on the topography you give it. So you give it a digital elevation map, like in the tutorial, they pre-prepare some of that for you. And it will calculate what is the slope of the HRU, what is the length of the channel, what is the slope of the channel, what is the slope. So it does all of those calculations for you. So it fills in slope for every HRU. It fills in slope for the subcatchments, slopes for the streams, sizes of the HRUs, sizes of the subcatchments. You don't have to, it will calculate all of those for you, and it uses them in the process equations. You do need to give it land cover types and soil types. It has some databases of parameters, properties of different vegetation types that we'll look at. But you can go in and change all of those. And you can also change some of the topography ones manually if you find that you need to. But it has databases. It's good and it's bad. Like, it's helpful and it's dangerous a little bit, because it has a lot of parameters already in the software. So you never have to, you could just click run and it will use the default ones and it will run. But if you never look at them, you will never know if they're inappropriate or appropriate for your particular area. Whereas some other models, people who've worked with Acru, for example, there's some preloaded stuff you can choose from, but you end up having to look at everything before you're allowed to run it. It doesn't just put in numbers behind your back and then let you run it without knowing what those numbers are. Whereas SWAT tried to make it easy for you, but it does mean there can be lots of numbers in the model that you've never looked at and never decided on, and you didn't even know were there. And then they are there and you've run it and you might not know why it's behaving weirdly. So it has these parameter values about land cover properties, soil properties, and aquifer properties in the software that you can choose or change. And so that's all, it's really nicely documented on this website. So this is linked to the main SWAT site, but I put the link in again. If you go towards like documentation and background theory docs and stuff, you'll find yourself here. And I showed this the last time too, but it helps to look. So let's have a look at some of the land cover ends up being in databases. So there's a plant's parameters. This section on databases, this will explain all there's a database that has suggested parameters for vegetation types, lots of different vegetation types. But if you put in a new vegetation type, you would have to fill in all of these things for that vegetation type to run the model. So what I've tended to do before was take some of their existing ones, like they've got a general forest and a hardwood forest and a woodland and stuff, and then I modify the things. But this shows you all these different things that it would have about each vegetation type. So like leaf area index. This is the fraction of the growing season. If the vegetation grows and dies over a season, especially for agricultural plants that get replanted every year, there's like a growth curve for the vegetation, and you would say how long it takes to reach its maximum, then when is it harvested, and then when is it or if you have seasonal vegetation that grows and goes dormant in a dry season or a cold season, you can use these things to control that, because that determines how much water the vegetation is going to use, and the canopy interception that's going to slow down the rainfall and have some of it evaporate. There's also parameters around nitrogen and phosphorus that the plants use. There's parameters around the erosion, so we'll come back. There's loads of parameters. So these are the parameters around the vegetation types. So you can see them here, and they're all listed. There's a definition and a min and max of suggested value and the units. Then the same is for soils and aquifers. So like the aquifers have, the initial groundwater levels, the depth. Some of these will be filled in by the model itself, like the slope. I think the slope is, but you have your initial nitrogen concentrations. You have base flow rates. You have a recession curve for like how quickly the aquifer drains out. And then like if you were to click on one of these, it gives you more information about each person and the equation where it's used in the model. So this website and this background documentation is super helpful, and we'll come back to it a lot. It's, as I say, it's not critical for everyone to understand every little bit that's in here, but all of these numbers will be in the model. And so it is a good idea to have a rough idea of what's there, and different people will end up helping out or thinking about or looking at different pieces of this. As I say, I've set up a model of these catchments that work relatively well, and I had to look at all of these, and there wouldn't be time in our sessions together to go through all of them, but I wanted to show everyone where they are, and we'll think about some of the critical ones together. I just wanted to show you the soils as well. Yeah, soils. So there's all these, you end up with a soils property database. So there's things like bulk density, the hydraulic conductivity of the soil, portions of clay, silt, and sand, erodibility factors, things that affect the saltiness of the runoff, the electrical conductivity of the soil water, or the starting values, pH, those water quality things. And so there'll be a soils database that they have some default ones. There are some ones that I worked on that I want to modify from the Agricultural Research Council, ARC. But if people have other data as well to bring to bear on things like this, that would also be great. So as you can see, there's lots of parameters involved in the model. And then this part down here has, so if you go to any parameter on the website, you can click on it and it gives you a definition of it and a bit about how it's used. You can, if you, in terms of where things come in and how they're used as well, there are all of these, the background equations in the model about how everything is calculated. That would also give you the, you'll find the different parameters also are defined here, structured around the actual equations, and the sequence of, you know, runoff and evapotranspiration and soil water lateral flow, for example. So it shows you how the model is doing everything from this website. I think you can get the whole thing as a PDF as well. There was for the previous versions of the model, but this format's quite nice to go through. And I think it also lets some of the AIs find it so that they can help you there to have it on here. So to jump back, here we are. Yeah. So I wanted to show you, so we've been talking about how it breaks the structure of the landscape up into pieces. So these process equations and parameters that have to apply to HRUs and to channels and to aquifers. And then after you sort all of that out and you run your model and you get some streamflow output and some other, also the other outputs I mentioned earlier, like actual evapotranspiration and groundwater storage and stuff, you would then do a process of calibrating. So adjusting these parameter values, these like the soil bulk density and the depth of the soil and things about the vegetation to help improve your model performance if it's not doing so well against stream flow. So this is an example of that. Like this is an initial model on the left, and then I adjusted parameters. You're always going to have some places where you win or you don't win. Oops, sorry. But it got a whole lot better between this one on the left and the one on the right, where the blue dotted line is the model and the black line is the observed. So some events are over there's too much stream flow, and there's some peak events where there's too little, and that always happens because of limitations with the data and the model, etc. But on average, it's a much better fit, and the low flows and the recessions, you know, the time where it's coming down from a peak, look way better after looking at some of the parameter values and changing them. And as you get to know a model, you'll get an idea of which ones to start looking at changing first when you see what it's doing. Like, is it producing way too much water? Is it producing the right amount of water, but it's coming too fast? Like the one on the left, the water's coming way too fast. So there's a high peak flow, and then the low flow is too little. So the water's running off too fast, not enough is moving slowly through the landscape. It's all come out at once, and then the base flow is almost nothing. The low flows are almost nothing. Whereas that's not what's really happening in the black line. There's a slower recession after a peak, and there is some more base flow in the drier times. So if you see that that's what's going wrong, you can have that you'd be like, okay, I need to store more water. More water needs to end up sitting in the soil and flowing more slowly out versus all of it flowing quickly over the surface. So you need to then look at like how much is getting into the soil, how much is getting stored in the soil, versus how much is just running over the surface. And you try and fix these kinds of problems that way. And then you go through that process of, is it working well enough? And if it's for what we want to use it for, and if not, going back and doing this calibration process again, or changing something's major. So you kind of go back and forth. How good is it? And is it good enough? And there's different statistics you can use to help you decide some of these things.
Sorry, Julia, would you go back to that line graph?
Yeah.
So what's being shown here is analyses, or what has come out of after you running the model. Am I correct?
Yes. Sorry, I didn't explain the graph very well. Thank you for stopping me. So yes. So the blue dotted line is the modeled output of stream flow of runoff, in this case. It would give you cubic meters per second. You can also change it into runoff in terms of like millimeters of runoff per unit of catchment, but you could also pretend this is stream flow. It's the same measure. So the black line is the observed from a weir. And then the blue dotted line is what the model predicted for that same location.
Okay.
So you have these peaks, you have high flows and low flows. I should make the date access a bit better, but it goes from October 1979 all the way through to 2020 something. But yeah, so the labeling needs to be a bit different. So there's February, you can see February 2007 over there. This is just an example graph to show you that like how it can change, how the model output can change when you go and fix some of these parameter values. So when you set up your model, it has these values like that you put in of what you think is best for the soil depths for your different soil types, and the soil bulk densities, and the soil porosity, and also different properties of the vegetation, like how deep are the vegetation roots, how leafy is the vegetation, what season is it dormant. So all those parameters you put in, and then you run your model and you get your outputs, and you're like, oh gosh, it's giving me way too, like in this example, the blue line is like too high peaks, and the low flows are too low. So you can see the blue line is much higher than the black line at the peaks, and then in the low flows, the blue line is way close to like having zero flow. So the water in my model was running off too fast. And so there's nothing left for the dry season. Whereas the black line shows that there is a bit more left in the dry season than the model is saying, and the peaks are a bit less than the model is saying. And then I altered a lot of times it's a lot about the soils, and some of the parameters that determine whether the water runs off the surface of the soil or infiltrates into the soil. And then once it's in the soil, how much of it can move laterally down the hill slope, or how much of it is stuck there in the soil. So like the field capacity of the soil for people who work with soils. And also just the sheer depth and porosity of the soil. And then it can also be aspects of the vegetation too that will dictate some of this. So I worked with some of these different parameters, and I got to the model simulation on the right, where the blue line is much closer to the black line, particularly in the dry periods. You can't even really see the blue line because it's matching pretty well. Some of the peaks are off still, some of them are too high, but now some of them are too low. And it's very hard to match every peak. But the overall pattern and the overall amount of water is way better than it was after some calibration work. So I guess the moral of the story, like mostly the point I wanted to bring home is that you put in all these values as best you can, and then you run the model and you see what's wrong with it, and then you go back to them and you change them to try and make the performance against the stream flow more reasonable. So the simulation of stream flow gives you some information, because a lot of these things we don't have good certainty about the properties of the soil or the properties of vegetation when especially when we're lumping them for big units of the landscape. Like you can measure soil at one specific point, but then when the model, you're assigning properties to the soil for an entire chunk of hill slope, and like much larger region than you would ever be able to measure. So it's always going to be a bit uncertain what the actual value is over that big chunk of land versus the one hole where you measured it in. So it gets tricky. So like actually taking soil samples and aquifer sample, like borehole core sampling and all of that stuff, it does help you to be in the ballpark, but you can't unfortunately expect those exact numbers to work very well all the time, because you're generalizing over a much bigger area than you've actually sampled. So this is actually quite a big part of the modeling process. And a lot of this is part of what I'll be doing for uMngeni water, and be giving you guys a calibrated model, but it's good to know how it was done, because you may want to improve upon it over time over my initial, and I will, present the way that I approached it and what I did. But then once people get a hang of it, they can continue to improve it, especially as new data is going. Every year we have new kinds of data sources and all sorts. And you may want to adjust the format of the model and add a new land cover type that we didn't use in the initial one, and you'll have to parameterize that. So it's good to have an idea of how this is done. Not everybody's going to have to do every little bit that I mentioned, but I just want everybody to have an idea of what the process is, and at an overall level at least. Does that answer your question, Saneda?
Okay, I'm sorry, Julia. I was trying to raise a hand, but I remember that you're not able to see hands.
Yeah, please jump in, guys.
Okay, sure. Can I please just ask then, with the parameters that you put in, including your link covers and all the others, so how does then the model allow you to cater for the infrastructure that's there in stream? So your weirs, your bridges, low level and high level, like how with the different streams that flow into the main channel, and the infrastructure that's there in each, how are you able to make those noted on the model? And if there were, for example, with most of the low level bridges, you'd find the flow is like backflow now, because of either there's sediments, there's debris that's blocking off the flow, and the flow is more or less opposite, like backflows more than your normal flows, and that would affect the model, I guess. How do you then in the model like note those or cater for that, so that the calculations are aligned with the conditions on site?
Yeah, so that can be quite tricky. So a lot of these hydrology models, they represent channels quite simplified. Let me see, do I have it? Okay, yeah. Let me go back. I'll go more into some of the water quality. Like I have some. So SWAT it started out as a catchment hydrology model. It has a bit of catchment hydraulics, which is more what you're talking about in terms of like backflows and channel processes and structures in the stream. So SWAT is quite limited in terms of what it represents there. It focuses a bit more on what comes off of the landscape to the stream. And then once the water gets in the stream, it does do quite a few processes in the stream, but not to the degree that something like, I don't know if people have worked with something like Heckgrass or Mike River do, or those ones. So that's why, for part of this project, for some of the in reservoir calculations, Jason Hallows, I don't know if some of you might know him and have worked with him on he's doing more the overall project, but some of that, some of the outputs of the SWAT model are actually going to get routed through some bathymetry models as well to look at the bathymetry within some of the large reservoirs, because of some of these backflow and distribution of the water quality, like you get layering within the reservoirs because of temperature and flow, and these, like, I know Ananda Dam is really curvy, and also like there's things that cause the water quality distribution to be more complicated than SWAT will represent. But what SWAT can do, we can change, so for each channel unit, we can change the size of the channel and the roughness of the channel, which will change how high and low flows are handled and how sediment does or doesn't drop out of the channel or get moved to the next channel in the model. So we can change some of these dimensions to represent a little bit how many, like, we wouldn't represent each low flow bridge or crossing, and it doesn't really have the capacity for that, but you could change some parameters of the channel for this entire segment to try and account for that a little bit if we think it's a big factor for that particular output at the point that we can model it for. Keep in mind, with these channel units, it's being, each blue line here between a segment and another segment is being modeled as one unit with an inflow and an outflow, and then like a storage in between that things happen to. So you can't get, you get an input value and you get an output value, but you don't have any values, like specific values for any points in between. So we're not going to try and get it to match. We'll pick where we delineate subcatchments, and I've tried to do that based on where we actually have some monitoring data, flow monitoring data and water quality monitoring data that I was given from some of your databases. It was like a year and a bit ago. No, it would have been 2 years almost ago. So there might be some new points that we want to add. But there's no, we can't try and match everything at every point. And it doesn't have the capability to do that anyway. But the idea was to try and get it to do a decent overall representation of what's going to reach the reservoirs and why, like the balance between some of the point sources and the non-point sources. So what's coming off of some of the agricultural land and settlement areas versus the wastewater treatment works and other point sources we know about and can include. So I hope that answers a bit of your question, but another thing is that we will represent reservoirs, and we can represent like smaller farm dams if some of these low flow. So then it will treat it as a water body that the channels flow into, and that water body will have its own water balance. And you can have rules for like how high the wall is and how water, it will then keep track of whether or not it's overflowing or not, and what we can add, controlled outflow. If we have a time series of how much is withdrawn and sent to a pipeline to a city, or so we have some of those for like the transfers with Spring Grove and Albert Falls, and I might be getting some of this wrong, but I did get some of the transfers, time series of the transfers data between different reservoirs and put that in. So that can be represented, but in terms of smaller low flow crossings and other things, we'd have to be a bit strategic if there's any like really big ones that we need to adjust for, look at how to do that. Does that answer your question? Okay, see a thumbs up. I think it'll become clearer and clearer. We'll go through how different water body types are added to the model and what I've done for your reservoirs there, and see if there's other points to add. But it's a great question because it is something you guys work with a lot and would have other inputs for.
Sorry, Julia.
Oh, Yeah.
Just a quick one. I don't know if you've already covered this or it's gonna come up as we go. I just wanted to find out, like, how much observed data do we need for a reliable calibration? Like, the time period. Is 5 to 10 years okay, or do we need to go longer? And I wanted to find out, sorry,
No, go.
okay, as a follow-up question or a question into that, as to how do we handle missing or inconsistent flow data during that period that we have selected to model?
Great, really good question. So this is always the tricky stuff. So different weirs and stuff, as you'll know, have a different time lengths of data. I try you just want to go as long as you can and do the best as you can, because it's you're gonna make a model either way in this case. But if the longer the better, you'd usually want at least um, it's a tricky one because there are things that change over time, and if those changes are not represented in your model, you can't expect the calibration, like the observed versus the modeled, to match. So some dams were only built, like some dams may only be 8 years old, and if they're not included in your, or if they are included in your model, the period before that won't, the flows won't look good because the dam's in the model and it wasn't there in that period, sort of or there's been a huge land cover change or new transfers come online, and so the model does allow some things to change over the course of the model run. It can get quite complicated to put that all in. So you like sort of a medium approach is to find a decent amount of time where things were somewhat stable and calibrate your model there with those settings. And then you can do different scenarios of sort of adding and subtracting dams or changing land cover. But so there's a balance there. They do say like you generally want at least 5 years, if not more, because of some of the climate variability too. You have El Nino cycles and other things. So you'll have patches of dry years and patches of wet years, and then just general climate change as well. And so the longer the better, because then you can test your model on some of these extremes, because you want to know about the extremes in your scenarios as well. So I would say at least 5 years, but ideally 10 years to at least get an El Nino, some highs and lows in there. Yeah, people generally aim for at least 10 years, but then you do have to pay attention to how much changed in that time that might be major. Now, not every change, land use change, land cover will change, but it might not always be a huge, like such a huge impact at the larger scale, depending on the scale of the land cover change, like and the scale that you're working at, like the entire catchment of Ananda Dam, or but very like upstream or right near where the change happened, it might have some impact. So it always, a lot of this is kind of an art rather than a science in a way. It's like, well, it's like that you have to do things as best you can because we never have all the data that we want to, and the model can never recreate every element that we would like it to. So it's always a bit of a balancing act. But it's a great question, and it also has to do with the data, the rainfall input data that you have. And so for this project, we talked, I haven't talked with this whole group, but we've had some discussions and we want to use the HydroNet rainfall input for this iteration. And I think we only have that from 2019 onwards until now. If you start mixing and matching different rainfall input sets, which we often have to do, you'll expect that there'll be a bit of a change sort of before and like the dates on which you switch which rainfall data sources you're using, and it can get a bit messy and you don't expect it to be the same performance for both of them, and you have to do some bias correction too, because they will it's going to influence how much rainfall falls in different areas and what you apply to your model. So that's also a factor in how long of a simulation you do. So for this one, for the uMngeni, for this current iteration of modeling, it will be from, I think it's like water years, I think it's October 2019 onwards, is when that data set's available for. But it would be nice to model it for longer, if there was a rainfall input to do so. So it's also the rainfall input as well as this, obviously the stream flow output. Sorry, long-winded answer, but yeah, the more the better, but hopefully at least 5 years.
Thanks so much, Gina.
No problem. So these are the perfect questions, and it shows it does, yeah, so that people are starting to grapple with the details. You can help. We'll do this together. All right. To talk about, I wanted to move now to how water quality is modeled. And then we'll go through this. I'm not going to go through it in too much detail, and then we'll take a break, and then we'll start working with the tutorial and the software, the file structure and that kind of those aspects from the tutorial that came with the software. So we've been talking so far about how the hydrology is modeled, and the water quality is obviously very linked to it, and a lot of the same principles apply in terms of calibration, parameters, inputs. But just some things to think about there is that when we model water quality with a catchment hydrology model like this, it's going to use the same structure. So I brought this up already, but it's the same set of channel units and subcatchments and HRUs and aquifer units that we've been talking about. So what that means is that when we delineate the subcatchments and the HRUs, if there's specifically water quality aspects that we want to look at, we need to delineate things with those in mind, not only the hydrology. And then you add on these layers of equations to estimate how the different substances and pollutants move through this same catchment system. So the soils of the HRU, does it percolate down and get into the groundwater? Does it flow laterally? Does it flow off in the surface water? And then does it enter the stream, and what happens when it gets there? So for these HRUs and for these aquifers and for these stream segments, we need information on, and these reservoirs, we need starting storages and concentrations of the various things we're going to work with. So for sediment, it can also be like the sand, silt, clay distribution, like how much nitrogen is in the soil on day one, phosphorus, etc. And there are some suggested values, and then you can kind of do this warm-up run. I think I told you before, like you can do a bit of a warm-up for things that take time to come into balance. And then you have the time series of additions. So fertilizer applications, we're not always going to know that, but we have to make assumptions of what do the sugarcane farmers do, what do subsistence farmers do, very roughly. And I made some assumptions there before, and I'll check those with you guys. And those are things you can update over time. Once you know what the model takes, then it's like over time. I feel like what the hope is that this will be a system that people will like add to over a longer period. We're not going to answer all of this together now in this financial year, but at least when you know what it's doing, it can be projects to improve some of this information. And then there's parameters about the storage and the movement and phase changes and growth and death if we're talking about bacteria. There are parameters relating to all of those in the SWAT model that you can choose to tinker with or use defaults, which may or may not, like the default values, as I said, they're in there, it'll run, it'll give you an output, but they may or may not be appropriate for here. So you have to look at how the outputs are looking and where the problems might be and go in and fix things. And then it calculates what substances are going to get transported, as I said, in the surface runoff, in the soil lateral flow, and in the groundwater flow and reach the channel, and then what happens to the substances once they're in the channel or the water bodies. So it's very similar to what I was talking about with the catchment to water balance. You start having balances for these different substances. There's inputs and their outputs and their storages, and things can either sit or they can move. But it gets more complicated with water quality in that you have phase changes And what I mean by phase changes is people who work with nitrogen, probably there's like ammonia, nitrates, nitrites, there's denitrification. So there's things like the nitrogen can change forms and it can stick to the soil, it can be dissolved in the water, it can get into the air as ammonia and nitrite. Yeah, so and denitrification back to N2. So like things can change. Like with water, we're just talking about water. I guess there's evapotranspiration and turn into vapor, but with water quality elements, and then bacteria can grow and die. And so I think you guys work with this stuff. You're more aware of it than I am even, but these equations get a bit more complicated because you have to include, growth and death and phase changes in that count essentially as inputs and outputs to different storages. So SWAT has equations for these, for the shallow subsurface parts in the HRUs, and for the aquifers, and for your streams, and for your reservoir, your water bodies. And I'll show you. So it's using as I mentioned, it's using the same structure. It does mean that it also uses the hydrology, obviously. So you need to know how much water surface runoff you have to model this, and you need to know how much groundwater movement you have. So if the hydrology is not being well captured by the model, the water quality is not going to be good either. So we generally try and calibrate and improve the hydrology first, and then move on to try and improve the water quality calibration. But it does mean that we can't only think of the hydrology model first. We have to think about the structure of the model overall to account for some of our water quality questions. So like subdivide it, like if you've got a large area of sugarcane and some of it's getting irrigated very differently and fertilized very differently from some other part of it, then we probably want to have 2 sugarcane classes, for example. And now the national land cover map may not, it might just have sugarcane in general. So we need somebody else or someone else to sort of subdivide the sugarcane for us in some way, or make some assumptions. That's a random example, but we may not have all of the things mapped that we want, and so have to think about how to deal with that. So, and then similarly, in terms of model structure, if there's certain points where we don't have a stream flow weir, but we have a water quality monitoring point that's been going for a long time and has really nice data, we probably want to subdivide a subcatchment or a channel reach to that point so that we can compare the water quality modeling to the data at that point, even if there's not a stream flow weir there. So I did try to do that in the first round, but we can review those points as well and see if we want to add any new ones or take out some, etc. So while we are going to look at the hydrology first, we do have to keep the water quality in mind as we do the initial structure of our model. So just to remind again, like when we were talking about HRUs earlier, you have to think about the water quality relevant parameters for each one of these kinds of HRUs in a landscape like this. What are there any fertilizer applications? What's the sewage system like? What do we think in terms of nitrogen and sediment? I mean, this area has a lot of bare soil and people have cut onto slopes and stuff. So you'd want to represent that in a way if we're looking at sediment transport, which may not come immediately from just the slope of the DEM, might not these open soil areas kind of stuff. So when we're modeling water quality too, there's a lot of land management parameters that for these non-point sources that we can represent in our models, and SWAT has ways of representing a lot of these. So things like irrigation and tile drainage on irrigated land as well, or on agricultural land, crop rotations, fertilizer, grazing. So with grazing, you can also represent like the manure load onto a pasture. There's ways to do that. And then there's pesticide applications. We're not going to work with, I'll get to which water quality parameters are part of the current contract, but I'll also show you what SWAT can do if you want to add them later. And then urban land, there's deposition of various chemicals onto impervious surfaces, and those impervious surfaces might connect to the stream through like an impervious network, or it might flow onto pervious, like a green space area that would change what happens to those, to any nitrogen or E. coli, etc. And then there's sewage systems and leaks and septic systems and other point sources from urban areas that you might want to put in for the water quality modeling part. And SWAT also does, so then there's also in-channel and in-water body water quality processes that get modeled. So there's the non-point source additions from the landscape that are going to enter the channel network. And then there's point source additions that'll enter the channel network. And let's say each like channel line here is a unit in the model. So you have an input and an output, and then it calculates sort of what changes in between that input and output in terms of your water quality parameters. And similarly with the reservoir, it has the inflow and the outflow, and then it assumes the middle is evenly mixed, which may not represent the points that you sample in your reservoirs, because it's not really evenly mixed in some of these very big convoluted shape reservoirs, which is why that modeling is getting done. Some of that's getting done in Mike as well to track how blooms move through and where particular pumps are and that kind of stuff. But this just views it much more simply because we're doing a big scale, like the whole landscape feeding down to the reservoir. So there's a lot of processes that can happen in a channel as well. Things can grow and die. Things can settle in this channel bed. Things can change based on temperature as well. So SWAT does model quite a bit of this, but with a lot of assumptions, but more than I like when I learned than I was expecting it to do. So that was good. But then you do have to then parameterize all of these calculations. So there are a lot, we make a lot of assumptions here, and then we have to check how good it's turning out, how well it's turning out. So I wanted to pause here on just like how it's doing the water quality, like the water quality theory part of it a bit, and then I'll show you some of SWAT's. I can actually, this is a good point to also ask if you want to break here now, or I was going to show a few of what the sediment and the nitrogen and the phosphorus look like quite quickly. I won't go into the nitty gritty of it, but just how it handles it. So you can choose if you want to take a break before or after I show you that, and then we'll go into the tutorial part. But firstly, like any questions about what I've just been talking about with and how it links to the catchment model or the catchment hydrology model.
Sorry, Julia, could you go back to that previous slide?
Yeah.
So here, in terms of the inputs, I'm assuming such as the different land uses, we have common, what would I put it, pollutants that would be expected to come or run off from those specific classes. And then that would form part of what's inputted in terms of the model. Would I be correct? Or does it go down to that specific detail of what those are and what they could be?
It gets pretty complicated. I'll show you quickly. I was going to go into that in the next section, and I will, but it would calculate by each HRU how much sediment would come off, how much nitrogen would come off, how much phosphorus would come off, based on like a whole like the nitrogen cycle. So it models a lot of parts of the nitrogen cycle and the phosphorus cycle for every HRU, every land cover class that we put in. So let me pull up that. Let me pull up this flow. So it will calculate for every HRU, for every land cover type. we'll need to give the model an idea of if it has fertilizer applied, how much and when. And then the soil type properties will also then be taken into account. So the soils have information about, it makes assumptions sort of how much will stick in the soil based on texture, how much clay, often like a lot of pollutants stick to clay, organic matter. It uses the carbon amount to assume about the organic matter, but there's nutrients in the soil. So each land cover class has parameters around, particularly for nutrients, and then some properties of the soil. And then for each land cover class, we'll also have a lot of management parameters like fertilizer applications, what months of the year it's applied, what format it's applied in as well. And then it will, it will calculate how much comes out of the HRU and then route that to the stream. And similarly, like similar approaches for sediment and bacteria, but I'll go into those a little bit. Am I answering what you were thinking about?
Yes, no, I think it gives me an idea, yeah.
Yeah, and it'll become clearer and clearer as we talk more about it, but it is actually modeling how much comes off each HRU. So each land cover and soil and management combination unit that we make will have a what comes off of that in terms of our water quality. A lot of people say pollutants, but like sediment and nitrogen and phosphorus are also natural. They're not like only pollutants, they're also a natural part of the system. It's just when we have too much of them, they're pollutants. So I don't always know the word to use. It's not all like sediment is a chemistry. So I'll say substances, I guess.
Yes. Okay. So and then I guess the larger the HRU, the larger the volume type of thing.
Yes, the larger the volume, but it's also different HRUs will produce different amounts of runoff. So it will depend on like the runoff that's produced on the day. So if it's like it might be a large HRU and it might get fertilized a lot, but maybe it's on a flat area and the soil's very poor, like has a lot of storage in it compared to so it will actually take all of that into account. It'll look at how much nitrogen gets suspended in the runoff and how much runoff is leaving. And that'll all get summed up through the landscape to see what enters the stream from the non-point sources.
Okay.
So it follows the same path as the water, but it does have to work out what ends up in the water versus what gets stuck in the soil, or gets stuck on the vegetation. And that's different for nitrogen and sediment and phosphorus and bacteria and pesticides. But we're not going to be able to look at all of that in this iteration of the project. The focus is going to be sediment, nitrogen, phosphorus. And then I know the next priority had been pathogens, but that's still getting added. That was in the original SWAT model, and they've moved it to SWAT Plus, but they haven't released it publicly because they're still testing it. And I actually spoke to some of the developers about when it was coming, and they said we could even use this as a case study to help them look at it if we have some nice E. coli data for the stream. So we can even look at that and work with them as a side project to get the E. coli bit released in the SWAT Plus public release of the software. How are people feel? I see that it's 2:30, so we're an hour and a half in. I can go through some of the nitrogen and phosphorus stuff very quickly and then we break, or we can take a break now and I do that and then we do the tutorial. How are people feeling? People keen for
Yeah, the suggestion, but is we can go for a break now, then start afresh.
cool. Let's do that. Do people need is 10 minutes too short? Do we need 15? I can do it. I'm flexible, I think. Cool.
15, yeah.
All right, cool. Let's come back then at 2:45.
So,
Great. Thanks, everyone.
thanks.
I'll pause stuff until then. Hi, everyone.
Hi.
Hi. Hope people had a bit of a stretch. I
Yes.
see a hand up.
No, she was just indicating she's here.
Oh, like a thumbs up that you're here. Cool.
Yeah.
Right. Great. Let me just resume the recording. Right. Yeah, so welcome back. And before we took a break, we were talking through some of the, like an overview of how we go from a a hydrology model of a catchment, which has some also representation of channel processes in it, as well as like landscape hydrology. And then we add this water quality modeling layer onto the same structure. So I'm going to go a little bit through how SWAT does some of these calculations, both for the landscape and then through to the channel, and then a bit into reservoirs. This is more of an overview, and then as we dive in subsequent weeks to how do we do it for your specific areas, we'll get to know some of the parameters and some of the inputs for this better. But this is an overview to give an idea of SWAT's approach here. So I've shown this slide before, but coming back to it, so SWAT has these land phase processes, so the landscape processes. So there's the hydrology, but there's also the plant growth that interacts with it. And then it also models erosion and nutrient cycling. And then there's various pollutants that it can cover pathogens, SWAT still being added to SWAT Plus, as I mentioned, pesticides, heavy metals, and salts. And these other land management aspects that it also simulates in certain ways. So we'll get into how it does irrigation and fertilizers and stuff more in subsequent weeks when we look at the parameters we assign to different land covers. And that controls the runoff and the loads of sediments and nutrients and other constituents that enter the streams. And then we have the stream and water body networks as well. And these things do in reality have some back and forth feedback, but it's a bit limited in this modeling. So it tends to, everything runs, when it runs off of the landscape into the river, then now it's in the river network and the water body network. Which I don't want to delve into this too much, but it is a slight limitation, but not in most landscapes, but in landscapes where you have big floods, that sediment gets redistributed back onto the land over large areas, then you want to have a two-way feedback more. But in this case, it's mostly the land processes, then flows into the river network, and then it does subsequent process in the river and water body network without from there on. And that controls the amounts of water and the loads of sediments and nutrients and constituents that are reaching the catchment outlet and reaching different points that we get outputs for. So it's using that same structure that we talked through with subcatchments, streams, HRUs, aquifers, and the linkages between them. So then for the landscape processes for sediment modeling, some of you might have seen this a long time ago when studying before, or you might still work with it now. There's the universal soil loss equation, which it's a fairly empirical method of estimating soil loss, but it's been used for so long by so many people that there's a large, you can find parameters that work, that get the outputs to be fairly reasonable from it, and it gets modified. It's been modified over time, so it's this modified universal soil loss equation now, MULSA. So there's the equation there, and you have these parameters about the soil type, about the land cover, about the topography, and about the coarse fragment cover, because they find when you have a lot of big rocks on the surface, it prevents erosion to some degree. But what to notice there is that this would be used for every HRU, so every land cover soil type slope combination unit, which it would calculate how much sediment is leaving in the runoff, the surface runoff, in each day of the model run. But you'll notice the amount of sediment that leaves, that's as calculated, is dependent on the amount of runoff that the model calculates for the HRU. So it does the hydrology and calculation, like how much surface runoff is produced on this day. And that gets used in determining how much sediment is carried off. So that will, Sanele asked before, like, is it considering the area of the HRU? So it consider the area and the slope and the land cover type and the soil and all of that to calculate how much water is leaving on this day. And that will be used to determine how much can erode. And it'll also account for the soil type, like how much can erode given the slope and the soil factors there. And then this gets routed, it'll get calculated for each HRU, and then we have that routing of the upland HRUs across the floodplain HRU, or all the HRUs in that unit, floodplain unit, and then from there to the stream channel. So you have this opportunity for a buffer that could catch sediment on the way to get represented. And SWAT has some other, because SWAT didn't used to route things this way. It used to route everything individually to the stream, but you used to be able to add a little buffer module. They wanted you to be able to represent the effect of having a vegetated buffer between a eroding area and the stream, because sometimes people want to test that as a scenario. So there's different ways of representing that. Buffering of the riparian. I know some of you working in catchment management and ecological infrastructure, and so you might be working with what's next to the stream versus a buffer area. Sanele, did you have a question?
No, sorry, I just forgot to mute.
Oh, no worries. I know you don't have to stay on mute. I just saw it light up a little bit. Cool. And it will take into account the particle size distribution of the soil as well. So, and it looks at the particle size distribution because in part linked to the other water quality parameters, because some things stick onto clay more than sand generally. And then it gets rooted, as I mentioned. And also smaller particle sizes lift off more, so it does your initial soils for all your HRUs will have percent sand, silt, clay, and organic matter. And then what gets eroded off, it has a mobilization factor for each one of those to work out what's the runoff distribution of sand, silt, and clay. And then that will get what ends up entering the channel. It'll look at the water flow and the velocity of water that it estimates for each channel using fairly simple hydraulics compared to something like a Heckras or a Mike River. But it allows you to calculate much larger areas in a much smaller amount of time. And so it really depends on the detail that you really need. But you can still get a decent output from this at that scale. As I say, so it'll calculate these flow through the channel unit. And so it has the sediment incoming, and it looks at what's the flow velocity in that channel unit for that day and what sediment has arrived. And, if it's slow, if the water's slow flowing and the sediment, there's a lot of sediment and a lot of its large particle sizes, some of it will drop out of suspension and deposit in the channel in the model. If it's very fast flow compared to the amount of sediment that's there, all of it might just get moved to the next channel unit. And if it's super fast flow and not very much sediment arriving from the landscape, it could even model erosion from the channel bed. So the channel bed also in the model also has a sand, silt, clay distribution optionally, or it can just assume there's two different settings you can put for the channel erosion and how much detail you want to go into it. It'll slow the model down to do the detailed one if you don't need it. If you do the simple one, it'll just assume that the channel bed, if you have a very low sediment load and a high flow, like there's infinite sediment in the channel bed to be lifted up and taken away. Otherwise, there's a more complicated one that actually tracks the channel size, and the channel can actually get deeper and wider in the model as sediment is removed. If you have these high flows with no sediment coming from the landscape, then the river will eat into the channel bed. And so SWAT can do that in a limited way. For people that there are like really detailed, what they call fluvial geomorphological models that look at that in detail, like how the shape of the channel will change over floods depending on the sediment movement and stuff like that. This is not that, but it does a very simplified version of that if you want it to. I haven't played with that part. I think it would slow the model down quite a lot, but we can look at it if needed. I've used the simple one before, which doesn't sort of track changes in channel shape, but it will add some sediment to the river flow from bed erosion if the flow is really high. Again, all of this is covered in like lots of detail for people who are interested in individual parts. That website has like all the theory and the equations and everything. So I'm just doing like high level, well, medium level overview. So that's the sediment movement part. So you have erosion from the landscape and transport through the channel, and potential deposition through the channel, and potential for erosion, the bed to erode as well and add sediment into the water. Now to turn to nutrients, I mentioned that SWAT does model plant growth as well. So it does look at the plants uptaking nitrogen and phosphorus, and it does look at plants dropping leaf litter, and also if things get harvested and the harvest gets like they only take away the grain and they leave all the leaves and the stems and stuff, or like I think with sugarcane as well, leaving the residue on the land or not, that gets added back into the nitrogen and phosphorus. It was because this was developed by Department of Agriculture in the United States. It has a lot of agricultural process representation. Similarly, actually with ACRU at UKZ, and the agricultural department was involved, and it has more crop representation than other types of vegetation. So that's part of the way that will get it represented to a certain degree in the nitrogen and the phosphorus cycling. And it does, so in the soil, it does represent quite a bit of the nitrogen cycle. I'm not going to go into all of this because there's a lot and it would take a while, but just to know that it does look at transfers between soil organic matter and the different forms of nitrogen. And it does include some representation of when the soil goes anaerobic. So that can be important, like wetlands. A big value of wetlands is the fact that there's anaerobic conditions, no oxygen in the soil. And when there's no oxygen in the soil, nitrogen gets removed instead of, there's bacteria that use nitrogen instead of oxygen, and it serves to can clean the soil water if there's extra nitrogen in it from fertilizers and stuff. So that can actually get represented in the model, which is nice. And so it does all of this to calculate how much nitrogen is going to leave each HRU in the surface runoff water, what's dissolved in surface runoff water, what's in the lateral flow, and what moves out of the HRU into the aquifer. And then the aquifer gets treated as kind of a tank as well. So it gets equal, if it recharges into the aquifer, then it's equally mixed, and the groundwater flow out will have that concentration of nitrogen in it, in the different forms. So it also tracks nitrogen in sediment. And so when it does the erosion calculation that I mentioned before, it will attach some nitrogen to that's in the soil organic matter nitrogen form. And then, so it tracks actually in each HRU, it's going to track these 5 forms. It has 3 forms of organic nitrogen, like fresh from the plant residue, and then this stable form in the soil that sits there more resistantly, and then there's decay, and you get this other pool of more broken down organic nitrogen that turns more easily into nitrate and ammonia, and then nitrate and ammonia can then get washed away, and then the organic form can get washed away in the sediment. The other ones can get washed away and run off and recharge, like can percolate down to the groundwater. So it does quite a lot of calculations on these nutrient balances, and there are a lot of parameters about this that we often don't know what to put in, but we can look at having some actual field data of what's in the stream at different points can give us information about whether or not we're getting some of these parameters right. And fertilizers can play a big, quite a big role there if people are fertilizing close to big rain events and that kind of, so putting that in there is helpful to know. So then similarly, so for phosphorus, it's a similar story, but phosphorus doesn't have as many forms that are soluble in water. And so a lot more of the movement is what's in the soil. So the erosion calculation again comes in here. So it tracks some phosphorus attached to the sediment that moves. And then it does look at the organic matter particularly. And then it does look at some of the inorganic phosphorus. Again, it has these pools of and there's processes that decide how much is in each one of these pools from plant residue and fertilizers being added, and a process of decay. So each one of these arrows in these diagrams, there's an equation that governs which way it goes and how far it goes, like how much moves from one to the other to the other. And then how much that goes into how much is going to end up leaving the HRU in runoff, lateral flow, and leaching into the aquifer below the HRU. So then you have all of those that's being calculated by each HRU and then getting routed to the stream in the surface runoff, in the lateral flow runoff, and in the groundwater then from that groundwater tank that gets some leaching down into it. Then once it gets to the stream, each stream unit is almost seen like a reservoir in a way. It's like a pool. It's how you have the inputs, and then you have processes that happen within the stream reach, and then you have the outputs at the outflow end, and it allows some of what's sorbed onto the sediment to settle if the sediment is settling in the reach or go through, and then there's some movement back and forth between the different forms of nitrogen based on parameters you assign to the stream channel. So it tracks in the stream, it tracks these forms of nitrogen, dissolved oxygen, carbon, phosphorus, organic phosphorus and dissolved phosphorus. And then there's the chlorophyll A and algae equations, but there's back and forth with all of this as well. So I'm not going to go into all the equations. They are documented on that website that I mentioned, but we will come back to some of the parameter values that you have to input for the stream channels that control how some of this works. Not today, but in subsequent days when we look at model setup for the uMngeni catchments. And then there is some feedback with the sediment layer of the channel. And then this is the same actually for reservoirs, but they just flow through slower because there's the wall blocking the output, and so it treats it like an equally mixed tank that has these processes going on in it as well, or like these pools of nutrients and sediments and the processes going between them. So it's a lot that it's calculating, and we're putting in a lot of parameters. But what's nice is that you guys actually have some data of what's in the stream and some data on the point sources. So we can actually look at how well it's doing, because not like more data than a lot of other parts of South Africa have on all of that. So we can have a look at how well it's doing these calculations. Then I mentioned it also does pesticides and pathogens in similar kinds of ways. Not as complicated as the nitrogen cycling, but you would give it, how much is being applied in terms of pesticides and also in terms of manure for the pathogens. And you could also look at how in more urban areas too, if you wanted to sort of assume that if there's not good sanitation, you could apply some E. coli across the surface that gets run out, that would then get washed off with the runoff, for example. And it would consider, do these things stick to plants or soils or get dissolved in the water? And there'd be parameters that would describe that for the pesticides and the pathogens you want to work with. And do they degrade over time? Some pesticides do degrade degrade over time, especially, and more so when they're dry than when they're wet sometimes. So you can represent that. So there's optional things you can add to represent that. And then with pathogens, do they die or grow as well? So it's not like input and output. Clearly, it can actually grow, like bacteria can multiply in between. So you can account for that, or it could die. And that can be temperature based and how much organic matter is available as well. So there are equations to govern all of that based on the climate and the soil properties and how much water is in the soil and that kind of stuff. And then it's how much leaves each HRU, given the surface flow and the lateral flow and the groundwater recharge that the HRU generates. And then would end up in the stream and point source additions to the stream as well. And then you have your in-channel and water body processes for pesticides and pathogens. Again, they can settle out, they can degrade, or you can have growth death. And there are equations for all of that. So there's, you can see there's a lot of equations here. Oh yeah, and this is just showing that in another way, the in-stream pesticide processes, for example, you have degradation settling into the channel bed, and then it can get suspended. So in a low flow time, you can get, and this is the same for nutrients, sediment, things will settle, and then you can have a big flow that can pick it back up. So the model can actually track that. It has a sediment store for the nutrients and the pesticides, as well as the sediments, obviously, and then when you have a big flow later on in the time series, some of that can get resuspended. So in terms of the model that working on for uMngeni water, sorry, I keep saying uMngeni water, I know it's uMngeni uThukela water. We're including sediment, nitrogen, and phosphorus, and the carbon and dissolved oxygen also gets, and the dissolved the biological oxygen demand also get modeled as part of that anyway. The pathogens and E. coli part of the model of the earlier SWAT model is not yet in SWAT Plus, as I mentioned, but it is going to be added soon. And when I asked the team that does the coding when that might happen, they said we can help if we want to, so we can if we have some good case studies, because they've done the recoding of it, but they need to test how well it's working in some case studies that they can look at against data. So that could be a nice thing to look at after we get through the basic setups for the other and get a reasonably calibrated model. And then pesticides again as well. That is, I believe that's in SWAT Plus now, but it's not part of what we're going to look at in this round. But the model structure, you can add any of these to the model that we'll build fairly easily. It's just sort of a question of looking at deciding to save the outputs, and there's some things you have to turn on in the software, and then you'd have to pay attention to what the parameters for the inputs are for these things, and then it would be in the model. So it's not a big structural change to the model to add them. So that's what I was planning to cover for today around the water quality modeling part. As I say, all of these parts we'll come back to as we look at the setting up the model for our catchments. But I wanted to introduce all the ideas before we get stuck into the software nitty-gritty stuff.
So just to ask you, so in terms of those once-off incidences, in terms of your source point pollution, that wouldn't, or there's no way that modeling can be factored into a model in terms of like certain incidences that could occur.
Yeah, so for point sources, so it gets tricky about what kind of incidents you mean. So like for a point source, I didn't talk about that as much, so that's a good point. So for point sources, we input them as a time series. Let me go back. Yeah. So I only really mentioned it there, but like point sources, we can import in the data, we can input that. Yeah, I didn't have a slide on that. Okay, good point. So for point sources from like wastewater treatment works and any other point source you want, if you have a time, you input it as a time series of data into the channel. Let me find a picture with the channel network diagram in. So for any channel, like each, can you actually see my cursor on the screen? Can you see my little arrow? I don't know if only I
Yes,
can
no,
see
we
that.
can,
Okay,
yeah.
great, perfect. Okay. So like each channel reach, you can add point sources of nitrate, like, and you would specify, is it nitrate, is it ammonia, what form is it coming in, phosphorus, sediment. So you can have inputs of water and that have nitrogen loadings in them. They have the concentration, how much water is coming in, and the concentration of nitrogen and phosphorus in that water from a point source can be added to any channel reach or channel unit in the model as a time series. So every day in your run, you could have it standard. You could say, you can put it in as a time series where there's a value for every day. So if you have the outflow from your wastewater treatment works day by day as it's measured, you would put that in. And so if there was a recorded, like there was a problem with the system and the concentrations recorded coming out of it were higher on a particular day or week or however long it was, you can put that in the time series file of the point source input into the channel. If you have information, let's say it's not so controlled and it wasn't actually monitored, but we have some information or we can make some assumption like it was, like we'll have to think about how, I know there's things like sewer overflows and other things like that where you don't know the quantity and concentration entering per day in the same way that you would from a monitored outflow point from a wastewater treatment works. But if you can estimate how much it might have been, we can put that in as a time series. As a point source, and it can be like, the time series can be nothing, a lot for 3 days, and then nothing again. In the case where you have a stream flow, like you have a stream reach that doesn't have a wastewater treatment works on it, and it does have, but there was a sewer leak, on this particular week in November, we could have a point source time series file that has nothing most of the time, and then it has an outflow of whatever amount we think is reasonable. So you can put it in that way for individual events, but you need to have an idea. There's no way for the model to know what the outflow in that event was. So we would have to make that up or like work out what's a reasonable time series of that outflow and concentration and put it in. Does that answer your?
Yes, okay. So it's one that we can, I think, feed it that data in terms of what sort of past occurrences have shown us. Yeah.
Yeah, and that's that'll be because one thing when I was trying to do the modeling before, what I put in for point sources were the large wastewater treatment works that I was giving data on, but I didn't put any data on, like I didn't have any data on particular sewer leaks or those kinds of things. And we can think how to do that based on, what information you have. But what you end up seeing, because there is stream flow, you guys have monitoring data for different points along the streams, and there'll be spikes that the model wouldn't recreate because it wasn't coming from anything else. There was a sewer leak and that wasn't represented in the model. So we can even add them sort of afterwards when we look at how it's performing. And then we be like, oh, it's not, there's actually a big increase in nitrogen in the stream flow data that the model's not picking up. And then you'd be like, oh yeah, we actually recorded a sewage spill or something on these days. And we'd be like, okay, we actually have to put it in the model if we want it to catch that. So we'll see what we could put in to start with, but it might also be a process of looking at the data and what gets missed and then going back and adding. But Because the tricky thing is like we don't, there's a lot of things we won't have enough information on, and it's never going to be the perfect model. But I think part of the point of trying to do this is to get a handle on how much might be coming from landscape sources versus like point sources versus non-point sources. And then if we have an idea of that, and if we have an idea of that, you can look at questions of like what might happen in a particularly large flood or a particularly high flow scenario, wet period scenario, as maybe as a forecasting to like, a wet period's coming and we know how much extra nitrogen and phosphorus you might expect to arrive at an underdam because of the runoff that would happen off of agricultural landscapes, or if things tend to get sewer overflow. The other thing we can add too as well, if like, there are areas that have the way the sewage and the drainage and stuff work, that when you have a certain high flow, a high runoff off of that area, you end up getting a lot of transport to the river, just because like the system gets overwhelmed. We can try and see how to put that in with some of the urban area routines. Is that answering?
Okay. Yes, no, because I think in terms of data, because we have champions that actually monitor sewer blockages and leakages in some of the catchments, we can provide that data, but what they usually collect or capture is just literally the incident, and then there's an app that we use that literally captures the start date and the end dates. So they open and they close that specific incidents depending on the many times that they frequent it, and see that it's fixed or not fixed. Once it's fixed, then they close it. So we've got a date and sort of a timestamp on each of those incidences, but we don't have the specific sort of volume that is sort of flowing out from each. But I think, yeah, that's one that I think would be a shortfall. But we do have that data in some of the catchments where they are situated.
Okay, that's great, because I mean, yeah, it would be very hard. I can imagine the flow, like there wouldn't be an easy way to measure the flow of that maybe anyway. But what we can then look at is, if you know the dates, we can look at where's the nearest stream flow monitoring point, and hopefully there's some data for those dates, at least for some of the events. And we can try and get an idea of if there was a pulse that we could see. And then you can play with putting it in as a time series input into the stream and see if we can get it to recreate that. With a rough idea of what the concentrations might be. And then it would tell us if we were way off, and we can play with it from there. Yeah, so I think we can try and represent some of those things. It won't be exact, it's going to be quite rough, but it definitely help to know the days when that's happening and look at what the water quality data. I don't know if anybody's already looked at that kind of, like, looked at when those events happen. Has anybody gone and looked at the nearest water quality monitoring points and seen what happened there?
Yes, yeah. So we do and can correlate that. It just depends on the catchment. So for the one that we're in now, which we're situated in here, in terms of the Msunduzi, is highly monitored in terms of water quality, because we've got like several what do they call them? Sampling points where we I think weekly to bi-weekly samples are taken in those areas, and then we correlate that with the data that we have in terms of the reported incidences. And there's, in most cases, a direct sort of correlation in terms of a specific incident and then there being a pickup in the we all usually use E. coli as an indicator in
Yes.
terms of the water quality within that area. But due to, I think, some of them not being fixed, it's sometimes difficult to see if there's a change because they are left unfixed or unrepaired for quite a long period of time. But yes, the correlation is there.
Okay. Okay. No, it'll be great to try and add those. So it's good to know that you have like the start date and the eventual end date or non-end date, or we can look at where those happened. And
Yes.
so we'll come back to that. That's great. So what I'd hope to, let's see. Oh yeah, okay. It's 3:20. I'd hope to go through more where people got to with the tutorial from now. But before I do that, do other people have questions on this that are sitting at the edge of their tongues, edge of their minds, before we move into the tutorial? Because the tutorial does leave the water quality part of it. It's getting more into it's just mostly looking at how the software functions from a interface point of view. And everything here will come back around again and back around again as we get into details. But does anybody have any water quality sort of conceptual questions at this point? Oh, I see a hand.
If I may, Julia.
Yeah.
Okay, thanks. I'm just trying to check then with the outputs of the model. So I've seen some maps. I'm just not sure whether there's other different representations of the output. But I'm just trying to check here if the model is actually able to alert you of the different trophic status in the water resource. So maybe if we were getting to a stage where we could be experiencing your algal blooms and stuff, are we able to either get that represented in the model, or we would get the pics in terms of the line graphs end and end? That would be more or less guidance towards what could be happening, and not exactly the different levels, trophic, your meso, hetero, and all the other different kinds.
Yeah, so the outputs will, let me come back to this. So the outputs for the streams, it will have concentration. So the outputs will be time series for each channel reach in the model, or each channel unit in the model. There will be a concentration it'd be time series of organic nitrogen, ammonia, nitrate, nitrite, dissolved oxygen, BOD, organic phosphate, dissolved phosphate, chlorophyll A, and algae. There can be outputs on every day for each stream reach for each one of these. So what you'd have to do there is come up with a classification when we're going to call it. And that's something the model won't do it won't classify that for you. It'll just give you how much flow is there and what's the concentration. So but there are some tools that other people have developed to analyze the output. But there might also be classification systems that you apply normally to some of your water quality monitoring data, and we can run the model output through those same classification systems as you would use that you're already using. I'm not aware. So it'd be a question of how we want to analyze the output data to give these classes. Does that answer? I saw a thumbs up, so great. Yeah, so these are the perfect kind of questions, though, because we will have to say, okay, it's going to spit out these time series for each channel reach, but then how do we want to analyze that? And a step I'm hoping to get to with the group, probably only going to be in our sessions in January, most likely, just because I'm working on some of this too before I send it over to you. But we can write. I find it's easiest if we have certain analyses we want to do with the output data. There are some tools in the software interface to sort of go through and produce certain graphs and outputs that they've pre-made, but because they don't know what everybody wants, they're limited to some standard things, and they're nice. But if there's a certain set of outputs we want, what's actually quicker to do is to write a code in Python or otherwise that will quickly it'll take, because the model's going to spit out loads of time series files as text files for every channel reach in our model, and there might be lots of them. So if we want to say at this point, we want to look at the nitrogen and classify, look at all the water quality parameters and apply a classification and build a map. And you can write a Python script that will do those specific analyses that people are interested in, and then just run that each time rather than doing more manual steps. So if we identify certain output processing workflows that we want to do, I'm happy to help code those up and show the process of coding them. A lot of it, when I end up asking ChatGPT to do a lot of the coding for me, and then I see that it did what I wanted to, and then I actually did a lot of back and forth with it. But it's gotten so much easier these days than it used to be. So if you haven't done it before, it might sound scarier than it is nowadays, thanks to the AIs. But maybe everybody's doing that more often than I am. But I've started to get into it, and it does help a lot. And I think we can put together some codes that people can then more easily run to get some of these specific things that are of interest to various departments in the group. And then hopefully some people in the team feel happy to make new ones as you guys come up with new outputs you want to pull. As I say, the model is not going to be able to predict it's nice because it gives you a lot of outputs, but we have to be realistic about how good they are and careful about how we use them. So it can give you a lot of information, but it's not all right. So don't get too excited because there is a number. We have to look at how right it is before we start sharing it with everyone. Sorry, and Tommy, I saw a hand up.
Yes, Julia, thank you so much for that. I was just thinking, just following on Vuyo's question, like the model, can the model be used to determine the return on investment? Say, for example, it were to kind of be used for scenarios to say before an intervention, this is what the cost look like, for example, and then if we were to have, for example, a wetland to filter some of the pollution that is coming from upstream, this is what it would look like. Can it be used for those kind of I don't know, prioritization of interventions, and also just looking at what the return on investment would be like?
Yeah, it has limited capacity to do like a lot of the economics calculations and all of that would have to be done externally. But what it could do would be like if we'll have a land cover map that represents the current state that we input, and we calibrate the model to that. But then we can change the land cover map, and we can add theoretical wetlands in different places, and see what those would do. And then you'd have to sort of pick different, like what are you interested in seeing as an output? Because what it'll give us will be time series of stream flow, and time series of concentrations of these. I see it doesn't say sediment there, but it would be sediments as well as the various forms of nitrogen and stuff. And then you'd have to say what exactly would be considered a good return on investment, because it'll just be two different time series, with and without. But you have to then, what you would have to do externally would be like, okay, what level of change in nitrogen or sediment or dissolved oxygen, etc. And eventually we will be able to add E. coli. It's not there yet, but it's not too far off. Then you'd be able to say, what amount of difference would be worth it, and that what amount of difference would be worth it is not something that the model can help us with, but it will give you an estimate of the time series with and without.
Okay, thank you so much.
Welcome. Yeah, but that's exactly the kind of thing we're hoping this can be used for. So so land cover and also management change scenarios you can look at, because we'll be putting in some fertilizer application and irrigation and crop aspects of crop management to the degree that we know them. So can even, without even changing the land cover type, you can also change some aspects of management of the land cover in that way. Similarly, with urban areas, there's certain, like, how connected is the impervious area? You can, so there's things you can represent in terms of management there. And then you can also just make a new land cover map and input that and rerun it, and then look at the changes. So that's what I'm hoping to get to, actually, once we get a decently performing model, is that we'll look at what kind of scenarios to try out. So are people happy to move back to our tutorial, looking at the tutorial? I wanted to see, but before I do that, is there anything else arising? A bit of a gear shift.
No, we're good.
I think we're good for now. All right. So now coming back to our software. So we started this last time and we didn't get very far. So I wasn't sure how far people were able to go on their own in between. I don't want to assume, it sounds like some people did actually keep going quite far with it. I just want to get a feel from the room. How far did people go in terms of going through that example? Or the tutorial from that PDF document?
Yeah, not quite far on my side. I don't know for others.
Julia,
Yeah.
when I was on the road when the first session started, so I think I'm almost like a newcomer, as we were listening on the road, jumping on and off the program. So, but I'm going to be listening in on the tutorial. I'm sure this is in the books as well that you received this morning.
Yes, yeah.
Okay.
The
So I'm
tutorial
also
actually
using
comes
it.
with the software when you download it.
So, okay. Yeah,
Um,
so I'm going to be working at least behind the team. I'm sure I will get assistance from the team.
Great.
Yeah.
We'll go through some more of it now. I just wanted to get a sense of if I should, it sounds like I can just keep going from the, like, almost pretty much where we stopped in the shared session. It doesn't sound like many people got much further than that anyway.
Yes.
And just apologies to anybody who did. I mean, it's great. I think you'll get more of it too if you do spend some time of it on your own as well. So let me load that up. Sorry, that's the intro. I have to just share pop over to a different screen. Okay. So we were looking at this example, or this tutorial. Okay. So the tutorial, again, for people who are also joining fresh as well, the tutorial PDF, I also emailed a version of it that has a couple little comments that I added, but the document itself is on the website and it also comes with the software when you install it. So when you install the software, you'll end up with on your C drive, most likely, you'll end up with a SWAT folder, and then it has a SWAT plus folder inside it, and then in there is documents and so it says manual, but it has a tutorial. It's like a software user manual, and it has a tutorial in it. So that's the tutorial I'm talking about, and that's where it is. And it's also on the website, and I'll also put it in the Google Drive. And so that's the PDF document I'm going to flip back and forth between. I'm hoping everyone's been able to install the software. I'm not going to go back to that part today, but people can catch up, and there is people who've managed to do it in the group. Hopefully we can help each other if people haven't. And then I'm not also going to go back to starting the plugin in QGIS. But what the tutorial does, so the tutorial takes you through a basic setup of the model for a catchment. Now, the tutorial comes with an example data set that they already prepared for you. So a lot of the things that are, it's just to give you a taste of the software, but there are data preparation steps that they've already done for you that we would have to do to set up a new model that are not in this tutorial because they've already done them for you. But it's basically to give you a taste for the process of delineating streams and delineating HRUs and that upslope versus floodplain landscape unit delineation. And then you go through adding like pre-prepared weather data and doing a run of the model. So it goes through those steps for you, but I found it's helpful for getting a taste of how to interact with the software. So this first part is are you asking?
No, sorry, just
Okay.
forgot to mute again.
Oh, no worries, no worries. Please do, like, if I seem not to hear you, please just speak up again as well in case. So the tutorial itself, or the document, the user guide, it has notes on installation. And then this part 3, I said look at steps 1 through 6, but it's really 5 and 6. It's really 6 actually that goes through all the process of setting up the model. But these initial points talk a bit about where the structure and the location of the source data and the output data, and then the so 5 and 6 are about getting going with the actual model of the example with using the example data set. So I'm going to skip the installation part, and what we had done last time was going into QGIS and adding the SWAT Plus plugin, turning it on. And there's instructions to do that between points 1 and 2 here. Actually, I think, no, it's even 5. Yeah, okay. Yeah, no, they put that in 5. All right. Apologies. I have gone through this, but I forgot what order they had this in the document. Okay. So yeah, so getting the SWAT Plus plugin turned on is in step 5. So we kind of, the last time we actually skipped over 2, 3, and 4, and we went straight into 5. But I do want to step back a sec and look at some of this structure, because now that we've done a bit of this step 5. So in step 5, we turned on the plugin for SWAT Plus in our QGIS. So if you'd gotten through a bit of that last time, I would open up that QGIS project again, and you should see this SWAT Plus plugin symbol in your QGIS. And we started a new project, and I had some instructions about, a bit of a change of instruction compared to, well, it's not necessary to do this, but I have an instruction about where to put some of the files that I think will make it easier for ourselves. So I'll just go through that now. We made a new project last time, and we called it Robit, and the tutorial document has, you make a project folder. You have, this is the software folder. This is where the actual executables of the software sit, and various other tools and things. And it does have the example data sets in it. And it ends up on your C drive. And so this folder in example datasets Robit has the climate data, the DEM, the land use, and other stuff that they've pre-prepared for you. But then when you make your project, the tutorial suggests you put it in, you make a new folder called QSWAT plus projects. You can call it anything you want. And it doesn't necessarily have to sit in your C drive, but sometimes if it doesn't, I suggest just doing it that way because sometimes you end up with permissions issues. But it doesn't have to, it could sit in documents, but I have had, depending on how your computers are networks and stuff, so maybe if you are able to put it on your C drive, it can be helpful to do that. But you can call it anything you want, but it's where your SWAT projects are going to be, different from the software folder. So they tell you to make a projects folder, and then in your projects folder, when you start your new SWAT project, make a window. Oh, I think it's still, oh yeah, I have the window there already. So we're already at, yeah, so it'll have this new project. We made a new project. It asked where do you want to put that project, and we put it in QSWAT plus projects, and then you tell it to call it Robot. I'm calling mine Robot 2 because I've already done it once, but it made this folder, and this is now going to be my project folder. What I would suggest, oh, I made one inside, sorry. But what I would suggest is that you copy over that example data set, the input data, into your project folder. Because otherwise you're going to be going back and forth between a lot of different folders, and it's easier if you just have one that you're working with. So if I open up a second Windows Explorer for a second, show you what I mean. So in my C drive, I would go to SWAT, my SWAT plus folder, go to example data sets for the robot example. I would copy all of this. I would copy it and I would paste it in my projects folder for robot. I ended up having two nested folders. But wherever your project folder is, I would just copy all of this in there so that everything is in one folder and you don't need to navigate back to this example datasets folder as well as your project folder. Because actually the tutorial instructions don't always say where you're going, and it's just easier if everything's all in one, I find. So that's like a side note, but I think it's going to help us. And I put that side note actually in the copy of the PDF that I shared, and I'll share it again. So I put that side note here as well on the PDF. And so what we got to last time was this first step of delineating streams. And in this example, they have you burn in existing streams. So somebody else had already mapped streams and they wanted to make sure that the delineation matched that. So he burned it. It took a shapefile of streams that were in the example data in watershed shapes and added it here and said to burn in the existing stream network. And then what it within QGIS, it uses some tools to automate the process of delineating subcatchments and catchments. And so it wants to use the digital elevation map to find all the land that's going to drain to each stream. And so the network of streams needs to be consistent with the DEM topography. So the first step you do actually is putting in this DEM, and the tutorial tells you where you just navigate to it and you add it, and then it loads it in for people who weren't here last time. And then you add, this part is optional, adding an existing shapefile of streams. You can just let it delineate them itself based on the topography here. But what it needs to know to make this stream network is how much land, like, do you need to have runoff from to start generating a stream channel? And that is different in different areas. It depends how fine of a stream network you want to represent in your model. So if you say a very small area would generate a stream. Like in this case, they suggest these are the values they suggest in the PDF, and so it's 100 cells which equates to 0.09 square kilometers, or if we put it in hectares, it's 9 hectares. So a 9-hectare catchment area would start generating a channel. And a way to figure that out, you have to put these in, and they give you the numbers for it in the tutorial. And what I generally have done in other areas when I'm doing this is I start with numbers similar to what they suggest, and then I have aerial photography in my QGIS background, and I try and look at, like, do these lines go way further than where I can see a stream, or if you have a stream shapefile from your other work, like try and see, am I getting way more little lines, little stream lines than I normally work with, or am I getting way shorter, fewer lines than I usually work with? And you play around with these numbers until the stream network that SWAT is coming up with looks similar to what you normally work with in terms of streamlines. Is that making sense to people? How it's like what it's doing here, and when I say like the catchment area that it needs to make a stream.
Yes. No. So you're saying it, so it can develop ones just using what could I call it, sort of the baseline in terms of what we see as the green and the brown and the that shape file in terms of the topography, and then it develops it from that in terms of
Yes.
surface area and elevation and whatnot.
Yes. So when you have a digital elevation map, it's a grid file of elevate, like each grid cell has an elevation in it. Sorry, I mean, some people, I don't want to re-explain, but yeah, I'm getting it. Like it's what it looks at, it then makes it's doing quite a lot in the background from that digital elevation map. So every grid cell has an elevation, and it knows which grid cells are next to each other. So for every grid cell, it says, the next one, the next neighbor is further down. So water would flow from this one down to this one, down to this one, and it tracks what they call flow accumulation. From high areas down to low areas. And then the flow starts concentrating because you have sort of concave landscapes. It concentrates towards the stream channel and says how much land needs to come together, like how many cells need to flow from one to the other before you actually have enough flow to start eating away a channel. We're going to actually get a river channel here. Like, where does the headwater channel start? And then it makes channels from there following the topography. So I can show you, for example, so this says it needs 9 hectares of land need to have their runoff concentrated into a lowland, like 9 hectares of upland that are all sloping towards a single point. Then you start getting a channel that you want to actually include in the model. Is that making sense a little bit? It's like how the topography converges.
Yes, no, I understand, yeah.
So it in the background, it's actually looking at, like which cells flow into which cell, and once it accumulates, in this case, 100 cells worth together, which, because it's each cell is 30 meters by 30 meters, it's 9 hectares, it starts. So if I were to go to this point, the start of this stream, there would be 9 hectares, like the catchment area to this starting point would be 9 hectares. And then bigger and bigger and bigger from there. And so you have to, it asks you to decide what these numbers should be. And it ends up being a bit of something that you play with until it looks like the number of channels you want to represent in your model, like the channels that you actually work with and manage, and that, because you could make it really fine. I'll just show you if I make this. like actually for time, making it smaller is going to take a while to run. So I'll make it bigger. Let's say I made the channels and the stream threshold bigger. So now it needs more land to start making a channel. And then I click create streams again. So you can play with this until you get it the way you like it. So just remember what it looks like there. And it's going to make a lot fewer streams now. It's still thinking of them. It can take a bit of time. Should redraw it. Thinking about it. See, you'll see that shapefile, the blue, yeah, there's the new one. So you can see there's a lot fewer streams now than it used to have. So now there's a lot fewer streams in my model, and my catchment areas are going to be bigger, and there's going to be less channel representation. The land area is still going to be the same, but it will take longer to reach a channel because there's fewer channels. The land over here is going to be further away from a channel than it was before, and then the length of channel for those channel processes to happen is shorter. So it has some implications. And then if I needed a monitoring point that's now not, if I wanted a streamflow monitoring point, but it's now not on a channel, like I don't have a channel at that point anymore, then this wouldn't be a good delineation for me because I won't get any stream flow. The land will be represented, but the channel will not be represented if there's no blue line there. So you have to work out what, so I've done that for our areas, but that already, like I've played with how many square kilometers gave me channels that match, that at least cover all the monitoring networks. And we'll come back to that, but that's what this is doing. So let me go back to what they had, which was 100 and 1,000. That's the area that it is using to delineate the channels. Yeah, 100 and 1,000 cells, which is 9 hectares and 90 hectares. You can change the units that it uses based on what you want to. It needs to, all your GIS data that you prepare for it needs to be in the same projection for people to do GIS stuff. So if I go create streams again, it's gonna think about it. And it's gonna use this DEM and draw a stream every time draw a channel every time 9 hectares of area gets concentrated into, flows into one point. So now it makes lots more stream. So the streams, the blue lines are the streams, and the dark blue lines are the streams, and the light blue lines are the channels that it's made. It'll make a subcatchment for every time 2 streams come together automatically, but you can add additional points if you have a monitoring point in the middle that you want to separate out. So that would be the next step in our delineation, is the inlet and outlets file. And so you can draw them by hand on this, but if you have a set of points you want to use, and then it will also use every confluence between 2 streams to separate subcatchments. So
Fusile just has a question.
oh yeah.
Sorry, Joe, can I please just check here? So if you already had a Rivers layer or a Rivers shape file for the area of interest, does the model then allow you to add that as a layer as opposed to going for the delineation process that we are currently doing at this stage?
You can use it, so the way that you can add it, but the thing is the model needs, it's better for you to let the model delineate it itself, because I'll show you, it needs to know which stream unit, there's a lot of data that it produces about each stream unit for you. So if we open the attribute file of the streams, it has link numbers and which number is upstream and which number is downstream from each one. It also calculates the length, the slope, all sorts of things. So it needs all of this for its calculations of flow through the streams. And you don't want to make all of this yourself. and it automates making all of this for you. So what they suggest you do if you have a network, you can put in your own, you can do what they call burning it in. And so the tutorial has you put one in. So this yellow line is the shape file that they already had separately. And what burning in means is that it takes the DEM, and every grid cell that touches this yellow shape file of their pre-existing river drawing or river shape file, it will drop the elevation of those cells that fall along this line a little bit, such that when it does the automated one, it will follow that path in as much as it can if it drops if it drops those cells in elevation a little bit, such that the landscape moves, like the landscape sloped towards them. That's burning in. It just means dropping the elevation of the cells that lie along these lines. But you can see it still doesn't exactly match it, which may or may not be a problem. The model's always going to be a simplification. You could try and burn it in more to try and match it. When you get to flat areas, you often get rivers that meander like this. And I'm sure, and there's lots of those in your area. And it's like, if it doesn't match exactly, it is sort of how much of a problem is that? Because it's treating this entire length as one unit anyway. It's a simplified model, so like this length from here to here is one unit anyway. So how many curves and kinks it has in it doesn't really matter. The length will be the total length of this unit will be a little bit different. And you can go in and manually change the length from what it calculated for you if there are a lot of bends that it skipped and the length is actually really different to what this length is like. Like if it's missing huge, like it's missed this meander and this one, like if there's a lot of that, and so the total stream is actually a lot longer, the pathway is a lot longer than what it has, you can actually manually go in and just change the length of the stream instead of trying to redo calculating all this information of which unit is. You'd have to recreate this table exactly for your own shapefile if you want to use your own shapefile exactly. So it's generally not worth doing that, but we can do the burning in process and that'll make it a little bit closer. But as you can see, we burned it in here and it still missed this. And that's a factor of the topography data set. It's 30 meters by 30 meters and it came from a satellite. And so it's not going to match exactly what's on the ground. So yeah, so it's never going to match exactly. But yeah, but that is a good question. And yeah, we have to look at where it's important to match and where it's not important so much to match. So I can see we're almost at 4 o'clock again. We're back where we were. But I knew like this part, this initial part is, it does take a while to get one's head around. So the next part, I think we're going to spend next week doing more of this because everything we've covered so far was really useful. So I'm not sad about anything. I just thought we might get a little further on this part, but we have time because it is almost, yeah, it's 4. So it's time for us to end. So I think let's plan for next week to really spend a lot of time, like go through the tutorial, because it is just to get a bit further on it so that people are able to go further on their own, because some of this parts there might be questions about it. So my suggestion actually for people in between now and then, you can try and go further on this if you want to. What I'd also suggest is to I would suggest maybe spending more time on that website and looking at some of the background stuff on anything that you're particularly interested in or that you work with in terms of like what kind of parameters are going into this model. Does that make sense to people? I think we'll go straight into the tutorial next time and spending more time on it.
Yes. Okay. No, that's fine.
I think that's going to be better. I thought we were going to get a bit further and then I could be at a point where I would leave you to go on your own more, but we haven't gotten that far. And I think it'll be So yeah, if you are able, spend some time with the website rather.
Okay.
And we'll go through this more and start going further on next week. And then on what I'm hoping to do is also start looking at the land cover data sets that are available that we would use in the uMngeni water model. All right, I see that it's 4. And thanks everyone. No, this is great. And I'm glad like the questions that I'm getting really show me that people are understanding this. So thank you.
Okay, no, thank you.
Thanks, Julia. Thanks, everyone.
Thanks, everyone. Take care. Have a
Bye.
good weekend. Bye.
Same to you. Bye.
Okay. Oh, somebody's asking something?
No.
Okay, great. Thanks, everyone.